We are now going to take a look at some of the more quantitative aspects involved with acidic and basic solutions. So we want to be able to determine for many acids and bases the concentration of the proton ion and the concentration of the hydroxide ion. This can sometimes be written instead as hydronium ion, but it should be understood to mean the same thing. So that's how we write the molarity of protons as H+. And then we use square brackets around hydroxide to indicate the molarity of the hydroxide in a solution. So for example, let's say we had a 0.10 molar hydrochloric acid solution. Hydrochloric acid is a strong acid. It completely dissociates in water. So every 1 mole of HCl would give you 1 mole of protons and 1 mole of chloride ions. So it should make sense then that if we have a 0.10 molar solution, the molarity of H+ would be exactly the same. And this would be true for all the strong acids except for sulfuric acid, which has 2 acidic protons. So using the same logic, what is the hydroxide ion concentration for a 0.30 molar barium hydroxide solution? Well, barium hydroxide is also a strong electrolyte. It is a strong base. So this means that if I have barium hydroxide in water, that's essentially the same thing as 1 barium ion for every 2 hydroxide ions, because of the 2 in the formula. So in this case, if the concentration is 0.3 for the barium hydroxide, since there's 2 hydroxides for every 1 barium hydroxide, we would expect the hydroxide concentration to actually be double the barium hydroxide concentration. So it would be 0.30 molar times 2 which is 0.60 molar. We have seen already that protons can react with hydroxide ions and make water. Now, the reverse reaction can also occur, but it's only going to happen to a very small extent. So what that means here is, if we were to look at the equilibrium strongly favors the left side here, which is to say that most water does not break down into protons and hydroxides. That process of breaking down is called autoionization. So auto means self, so self-ionizing. So it turns out that if we look at water, about 1 in every 10 million water molecules at equilibrium will be autoionized. So it's an extremely small number. And so we would expect then the proton concentration to be 1 times 10 to the minus 7, and the hydroxide concentration to be 1 times 10 to the minus 7 molar. And this is the case if we have perfectly neutral water. So under normal conditions, typically meaning room temperature and 1 atmosphere of pressure, and we're not going to look at any other conditions, what we will find is that if we multiply the concentration of protons times the concentration of hydroxide, it's going to be a constant. It will always equal 1 times 10 to the minus 14. We leave out the units in this case because they would be rather strange. It would be molarity times molarity, or molarity squared. So this is an important constant to know. So what does this mean then? It turns out these two values are inversely proportional. So if the proton concentration gets larger, the hydroxide concentration would have to get smaller in order to always stay at 1 times 10 to the minus 14. So it's an extremely useful reaction when we're trying to come up with quantitative relationships for acids or bases. And the reason for its value is that if we know what the proton concentration is, we can always find the hydroxide concentration. And vice versa. If we know the hydroxide concentration, we can always find the proton concentration for any solution in water. Now, the problem with proton concentrations in acids and bases is that the numbers for this are often extremely small, so much so as to be inconvenient. For example, among the most concentrated acid solutions, we might have concentrations of about 12, but more often than not, we are dealing with numbers that can be very, very small. And so it's much more useful to use what we call a pH value, which is simply calculated from the proton concentration from this formula right here that you want to know. The pH is negative log of the proton concentration. So that's what P means here, negative log. Now, you might not be very familiar with logarithms at this point. The most important thing that I'm going to need you to be able to do is figure out how to use these in the calculator, but I will try to explain how this works as we go. So let's say, for example, we want to know the pH of this solution here. It's something which has proton concentration of 0.0145 molar. So to find the pH, we just take negative the log of this concentration. Now, depending on the calculator that you are using, this is usually the sequence of buttons that you would use here. So you would type in negative, usually the subtraction button won't work, log, and then depending on the calculator, it might give you an opening parentheses when you hit the log button. If it does not, you're going to need to hit the open parenthesis, type in the value that you want to determine the logarithm of, put on the closing parenthesis, and then hit either enter or equals depending on your calculator. So I'd like you to take a moment and try this on the calculator. So putting this in, so I have negative log, and then I put in my number 0.0145, closing parentheses. In my calculator, it gave me the opening parentheses, and then I hit enter. And what I find here, after using the calculator, is that this gives me 1.84. We're not going to worry about the significant digits for logarithms. They're a bit complicated, so let's just say we'll go to the hundredths place for logs. So you might not see the convenience of using pH in this particular case. We have 1.84 versus 0.0145, but as these concentrations get smaller and smaller, that's going to make dealing with pHs much easier. Suppose, on the other hand, we know the pH value, and we would instead like to find the proton concentration. We need to do the inverse of the logarithm, and that is called the anti-logarithm, or anti-log. And the anti-log is essentially just 10 to the power of the number that you're taking the anti-logarithm of. So for example, if we wanted to take the anti-log of -2, it's just 10 to the -2 power, or 0.01. So if you've had an intermediate algebra class, you'll be able to discover the important relationship here, which is that proton concentrations is equal to 10 to the negative pH value. So for example then, let's say we have a solution with a pH of 1. If we want to find the proton concentration, that would just be 10 to the negative 1, which could be rewritten as 1 times 10 to the negative 1 molar. We always want to get these powers to be to an integral power. In other words, it needs to be 10 to the negative 1, negative 2, negative 3, something like that. It can't be 10 to the negative 2.36 or anything like that. That's not allowed in a final answer. And that's the whole point of using the calculator's anti-log feature, is it will go ahead and correct the number to a more visually useful form. So let's say we wanted to find proton concentration for a solution with pH of 6.25. All you have to do is use your calculator and say take the anti-log, that would be 10, to the negative of that number. So 10 to the negative 6.25. So in the calculator, the way we could do this is we could say second 10 to the x, and I want to note that the 10 to the x operation, the anti-log, is most commonly right above the logarithm key. And because it's above the logarithm key, you need to press the second button or shift in some calculators to get access to it. And then you would type in negative 6.25, the pH, and equals or enter depending on the calculator. This would not be considered an acceptable final answer. You want to put it into the calculator and see what it comes up with. So let me go ahead and do that. So I put in my 10 to the power button and then negative 6.25 and hit enter. And I come up with 0.000000562. So I see there that there's a total of 6 zeros, but I want to get this into scientific notation. So this would be 5.62 times 10 to the negative 7 molar. Now, we already saw that for neutral water, the proton concentration is always 1 times 10 to the negative 7. And therefore, the pH of water is going to be 7. Now, it's very important to understand the trends here. As the concentration of protons gets larger, we're saying the solution becomes more acidic. Acidity is essentially based on the number of protons that we have in solution. So the more of these that you have in a certain volume, we say the solution is more acidic. If it was hydroxide, as this got larger, we would say that the solution would be getting more basic. Very important, as the proton concentration gets larger, the pH decreases. And in particular, as the proton concentration gets 10 times larger, the pH decreases by 1. So what that means is pH 5 is 10 times less acidic than pH 4, which is 10 times less acidic than pH 3. So we can use a nice scale here to look at the pH values. And let's construct that scale. So for almost all solutions in water, the pH is going to be between 0 and 14. There are possibilities below 0 and greater than 14, but for reasons that kind of go beyond the scope of this class, I don't want to address why it wouldn't be wise to really discuss these other pH values right now. So we've defined pH of 7 as neutral. Any pH which is less than 7 is considered acidic. Now, some people might argue and say, well, 6.99 is neutral, and it is in fact very, very close to neutral, but we're just going to say that less than 7 is acidic. And then pH is greater than 7 are basic. I've chosen these colors because we often test the acidity of a solution with litmus paper, and litmus takes on a red color in acidic solutions and a blue color in basic solutions. Now again, as we go further and further to the left on this line, we are getting more and more acidic. So, if we have, for example, pH 1, that is 10 times more acidic than pH 2. Again, when I say 10 times more acidic, that means there's 10 times greater concentration of protons than in pH 2. And pH 2 is 10 times more acidic than pH 3, etc., until we get down to pH 7, which is considered neutral. So we've learned some important equations, and we want to put them to use here. So let's say that we have a pH of 4.75 for a solution. Let's find the proton concentration and the hydroxide concentration. After that, let's look at another solution. So given the hydroxide concentration, we want to be able to find the pH and the proton concentration. So it's important that given any one of these three pieces of information that we be able to find the other two, and it's also important that we be able to say whether the solution is acidic, basic, or neutral. So in our first problem, we said that we have a solution with a pH of 4.75. And we would like to find the proton concentration and the hydroxide concentration. So we have to find the right equations to use. So we're given the pH of 4.75. Remember that the proton concentration is just the antilog of the negative pH. So that's simply 10 to the negative 4.75. And this would have units of molarity. I'll add them at the end. Negative 4.75 is not considered an acceptable answer, so we're going to have to use the antilog. So we say 10 to the negative 4.75 in the calculator. And this gives me 1.78 times 10 to the minus 5. Your calculator might not be so kind as to put that in scientific notation. Mine did not. I had to count those decimal places. And so, as I said, times 10 to the negative 5. So we've found the proton concentration. How do we find the hydroxide concentration? Well, for that, we're going to use this equation. We said that proton concentration times hydroxide concentration equals the autoionization constant, which is 1.0 times 10 to the negative 14. So we can rewrite this equation, dividing both sides by the proton concentration. And that gets rid of proton concentration on the left and gives us this equation here. The hydroxide concentration is equal to 1.0 times 10 to the negative 14 divided by the proton concentration? Well, we know the proton concentration. We just got that. So it's just a matter of putting these numbers in the calculator. So I have 1.0 times 10 to the negative 14 divided by 1.78 times 10 to the minus 5. And this gives me 5.62 times 10 to the minus 10. And the units would be molarity. You'll notice the pH has no units. So let's ask ourselves, is the solution acidic, basic, or neutral? Well, the pH is 4.75. That is less than 7. So if the pH is less than 7, that means we have an acidic solution. Incidentally, a solution can never be acidic and basic simultaneously. They're either one or the other, or the solution is neutral. The other way to determine that this solution was acidic is that the proton concentration will always be greater than the hydroxide concentration for an acidic solution. For a neutral solution, they would be equal, and for a basic solution, there would be more hydroxide than protons. Let's look at question 2. Question 2 said that we have a hydroxide concentration of 1.45 times 10 to the minus 4 molar. So we want to find the other three values. We want to find the pH, and we want to find the proton concentration. Well, which to find first? Well, it's probably going to be easiest if we use this equation that we just used a moment ago. So we saw that proton concentration times hydroxide concentration equals 1.0 times 10 to the minus 14. That should be true for all aqueous solutions and for water. Now this time we have hydroxide concentration. The unknown is proton concentration. So let's get rid of hydroxide ion concentration. We'll divide it out on both sides. And so, canceling out hydroxides on the left, the proton concentration is just going to be 1.0 times 10 to the minus 14 over the hydroxide concentration, which I'll just write here is 1.45 times 10 to the minus 4. So we have 1 times 10 to the minus 14 divided by 1.45 times 10 to the minus 4. And this gives me 6.90 times 10 to the minus 11. And while I admit we're being sloppy here with units because of the fact that pH has no units and that this would have a weird unit of molarity squared, we still do always want to write molarities for any of these values that are in square brackets here. So you'll notice that the proton concentration is very small. The hydroxide concentration was also small, but much, much larger than the proton concentration. Millions of times larger. Okay, so we found the proton concentration. Now let's find the pH. Go back to black here. And so here we just use the definition. pH equals negative log of the proton concentration. So that's just negative log of the answer that we have here, 6.90 times 10 to the minus 11. You'll want to be sure that you check this in the calculator yourself so that you're not making any errors. So I have negative log of 6.90 times 10 to the minus 11. And this gives me a much more manageable number of 10.16. And pHs have no units. So is this acidic or basic or neutral? Well, it's clearly not neutral because the pH is not 7. The pH is greater than 7, and that means that the solution is basic. The other way we could determine that is we could compare the proton concentrations and the hydroxide concentrations. In this case, the hydroxide concentration is much larger than the proton concentration. Which is what we expect for a basic solution. The last important topic I'd like to discuss in this chapter involves buffers. We define a buffer as a solution which resists changes to its pH when acid or base is added to it. As we see in the lab, if we take a solution which is neutral, like just plain ordinary water, or a sodium chloride solution, and we add a strong acid to it, the pH will plunge dramatically, even with only a few drops being added. If the base is added to this neutral solution, the pH will go skyrocketing to a very high value very quickly. A solution which is buffered tends not to behave this way. Adding acid only causes the pH to go down slightly, and adding base only causes the pH to go up slightly. So a buffer must contain two very important parts. It must contain a weak acid and its conjugate base, usually as the sodium salt. Or it can be a weak base and its conjugate acid. And to make things easy, I'm only going to consider the first case here, so a weak acid with its conjugate base. So let's take a look at an example here. So let's say we have a buffer, and it is made up of acetic acid, which would be a weak acid, as required, and acetate ions, probably as sodium acetate. Now I want you to think what happens here. What happens if we add some acid to this solution? I want to go ahead and write out some equations to show this, but before I do that, let's just preview the other questions. We also want to know what would happen if instead I had added base to this solution. And then I want to ask if hydrochloric acid and chloride would form a good buffer solution. Well, that's an easy enough question to address right now. Hydrochloric acid is a strong acid, and therefore this will not form a good buffer. You need a weak acid and its conjugate base. So we said our buffer solution contains two species, acetic acid, which is CH3, COOH, there's actually several ways of writing this, and sodium acetate, of which I only care about the acetate ion. So that would be CH3COO minus. Because remember, the conjugate base would be formed by taking the acid and depleting a proton from it. So, what happens if I add acid to this solution? If I add acid, it's not going to react with the acid. The acid's already an acid. However, this is a conjugate base. So if I add acid, adding acid is the same as adding H+ ions. What does that do? It converts some of the acetate ions into acetic acid. And so long as we still have some of the acetate ion left, what's in the solution? Well, it's the same solution. It only has more acetic acid now than acetate ions. So adding acid would, in fact, still keep the same chemicals in the mixture. On the other hand, let's say I added base in the form of adding hydroxide. Adding base to the conjugate base doesn't do anything, but the acid will react, and that would give us, guess what? Acetate ion. So again, and to keep things reasonably simple here, let's get rid of right here in the bottom so we can focus on the top. What do we have? So long as there's still some acetic acid left over, we have a mixture of acetic acid and acetate ion. Some that was there originally from the original buffer, and some that we've produced by adding hydroxide. So long as we don't add enough acid to completely react away the acetate ion, and so long as we don't add enough hydroxide to completely react away all of the acid here, we will still have a buffer mixture. In other words, a mixture that contains both the acid and its conjugate base. This can't happen for a strong acid like hydrochloric acid, because if it's a strong acid, we had said that it's completely dissociated. So you only have H+ ions and chloride ions in the solution. There is no intact acid. It's totally dissociated. With weak acids, on the other hand, we still have some of that weak acid laying around, which can be neutralized by the hydroxide. Adding hydroxide to a strong acid would only make what? Well, if you add hydroxide to H+, it just makes water. So it must be a weak acid and its conjugate base, usually as a sodium salt. Let's look at a few other examples real quick. So the very dangerous acid, hydrofluoric acid, is a weak acid. Its conjugate base, meaning after you take away the H+, would be fluoride ion. And as I mentioned, we usually use the sodium salt here. Although the only important part here is the fluoride, not the sodium. What if we used formic acid? Formic acid is a weak acid that we get when we are bit by ants. Well, you would lose this hydrogen at the end. So we need to have this here the conjugate base. Now usually we would write it as so if we had sodium. I know it's going to seem weird because we normally write the cation in the front, but because this is an organic chemical, which we will start to study in chapters 10 on up, you'll see that this is more customary for that. One more. Another very dangerous acid, hydrocyanic acid. It could make a buffer with sodium cyanide. So the acid and its conjugate base with the sodium there just to balance out the charge. Most of our body fluids are buffered in some way. Let's take a look at, for example, blood. It turns out that for us to remain healthy, our pH of the blood has to be kept at a value slightly greater than 7. If we deviate from that value by much, it can ultimately result in either injury or coma and eventually death. And so we all occasionally imbibe acidic drinks. So a soda, for example, has a very low pH. If we drink orange juice or tomato juice, that has a low pH. And obviously we're all alive, even though we have drank these acidic solutions here without a problem. So what this means is there has to be some kind of a buffer in blood. And in fact, the buffering in blood is fairly complex. We're just going to look at perhaps the most simple species of that. And that is the bicarbonate ion, which is present in the blood. And this is a very special type of an ion because it can act as both an acid and as a base. And so if the acidity gets too high, this can act as a base. And if the acidity gets too low, in other words, the pH starts to go too high, this can react and act as an acid. And so this keeps our pH of the blood in a fairly nice normal range. So let's ask ourselves then, if there's bicarbonate in the blood, what will happen if some acid is introduced into the blood? What would the buffer do? And likewise, what would base do? Well, in order to answer this question, we need to know something about how bicarbonate is going to behave. So let's say we have bicarbonate ion here. The acidic ion at the front is this H+ ion. So if we were to add some base, this would form the carbonate ion. However, since blood is buffered, we already expect some carbonate ion to be present. So we're not adding enough base in almost all situations here to completely get rid of the bicarbonate ion. So we have both components of the buffer. On the other hand, let's say that we add acid to this. So if we add acid, remember that would be H+. If this takes on another H+, that gives us this chemical here, which is carbonic acid. Now, carbonic acid, as I'd mentioned, is very, very unstable. Carbonic acid will very much favor decomposing into water and carbon dioxide. So if this is reacted with acid, it becomes carbonic acid which carbonic acid immediately will decompose to make water, which is already present in large amounts in the blood, and carbon dioxide, which we can then expel. If for any reason the amount of bicarbonate becomes too low in the blood, we can always react carbon dioxide with water to make more carbonic acid, which then in turn can react with any base to form bicarbonate ion again. Well, how could this happen? This goes back to Chapter 7 when we talked about Le Chatelier's principle. So, even though this is highly unstable, we would always expect there to be a little bit of it ready to be formed. So if there's not enough of this in the system, water and carbon dioxide, in order to maintain equilibrium, are pulled to the left to make some of this. That would then be converted into bicarbonate. Now we have a problem, because if we've just lost this carbonic acid, well, then water and carbon dioxide needs to make more, and so they make more carbonic acid. And then, if there is base present, that converts that to bicarbonate. And so you see this keeps going and going until we have enough bicarbonate present in the blood. It's a very complicated game of push this button and pull that lever to get everything in just the right balance, but our blood does that, and that is what keeps us alive so that we don't die every time we take a sip of lemonade. This is going to be the end of Chapter 8. Thank you.